So my goal is to one day identify life beyond Earth. And today I want to tell you how I'm trying to get there by studying all potential signs of life, even the really weird ones, and by trying to train the next generation to join the cause. So how does the search for alien life happen? Well, to answer that, let's try and reverse the problem. Could an alien civilization know that we have a rich and super cool inhabited planet? Imagine an alien astronomer on the other side of the galaxy looking for a habitable planet in their night sky. Now, if this alien astronomer pointed their very powerful telescopes at our sun, they would be able to split its sunlight into the sun's spectrum. And this is exactly what they would see. They would see that some of the light from the sun would have been absorbed by atoms and even molecules in the cooler regions of the sun where molecules can survive, and leave behind these tiny shadows known as absorption lines. And that's because molecules behave in a really unique way. I am a quantum astrochemist, which means I study how molecules interact with light and leave these shadow imprints, no matter where in the universe we might find them. And so I can interpret these sort of images. Molecules have to follow the laws of physics like we all do, but it's not quite the same physics that we are used to. Molecules are so small that their physics follow the rules of the quantum world. And one of those very strict rules is that molecules have to absorb quantized amounts of energy. And these correspond to specific wavelengths of the light spectrum and specific colors of the rainbow, as you just saw. Different stars have different compositions and consequently have a different spectrum. And this one is our sun's. This is our sun's spectral fingerprint. So those alien astronomers could look at the spectrum and, using their universal knowledge of molecules that they got from their quantum chemists, know exactly which molecules and atoms were causing these shadowy absorption lines and figure out the composition of the sun. But if they were patient and fortuitously aligned, they would notice that every 12 years, a few additional absorption lines would appear and then disappear, and then 12 years later appear again. And these lines would be due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. An alien civilization with only slightly better technology than we have now would be able to study these new lines and know that Jupiter has a huge, complex atmosphere with not just hydrogen and helium, but also methane, ammonia, hydrogen sulfide, and many more gases. And if they were really careful, every year, a few much fainter shadows would appear and then disappear, and a year later return. And these, of course, will be due to the molecules on our own Earth's atmosphere, also absorbing new lines of the sun spectrum. And that alien civilization could study these absorptions and know that we are a thriving, complex, living planet. These alien astronomers could use this technique to try and get spectra for all of the solar system bodies. For example, here we are looking at Venus, Mars, Jupiter, and the Moon, seen here from Earth. Even from this comparatively short distance, at least in astronomical scales, the light from these drastically different planets like these can appear really similar. But again, their light spectrum will showcase how different they truly are. By splitting the light of these solar system bodies, they would be able to see something like this. Because a spectrum is usually not represented by a rainbow, since those are pretty but rather impractical, and instead by a plot of light intensity varying across wavelengths like you see here. These alien astrophysicists could study the spectra from each of these different solar system planets. And if they did that, they would learn that Venus is mostly hell, with very high levels of sulfuric acid, so any life there will struggle, though more about that later. And they would learn that Mars has a teensy tiny atmosphere that can barely shield its surface from radiation, so also not the most hospitable destination. And they would know that out of the solar system planets, there's something really special about the Earth, and that is we have a lot of life. You can think of our atmosphere and its subsequent spectrum as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute a lot. By studying the light coming from our solar system, those alien astronomers would be able to know that on Earth, we don't just have an atmosphere, we have a biosphere, and we can do the same to them. Now, first, we do have to find the planets themselves, and we've been working on that for a long time. We found Uranus in 1781, Neptune in 1846, Pluto in 1930, and then lost it again in 2006. Then we found our first exoplanet in the mid-90s and kept finding more and more. With the Kepler mission, we found thousands of planets. And with a more recent test mission, thousands more. And with upcoming missions, we'll find tens of thousands more. So we're getting really good at finding planets. We have just begun finding atmospheres on these planets, and we still know very little about them. Future missions will provide more data on more planets and their atmospheres, which means we are now on the cusp of being technologically able to detect the molecular signs of life in these atmospheres. And then, what should we look for? Well, to find life, we can start by looking for signs of life as we know it. The easiest biosignatures or molecular markers for life that we can detect on exoplanets are beloved gases that we already know from our own life on modern Earth, and they exist in our atmosphere in reasonably large quantities. So these are molecules that life that we find pleasant loves to make, like methane and carbon dioxide, which are produced in large abundance by life. But we can also look for molecules like hydrogen cyanide, which are not particularly popular biosignatures now, but they are likely crucial as a building block of life. So it's a good pre-biosignature. We know of these gases already, and we can and should look for them on exoplanet atmospheres. And we can do that by looking for their own individual spectral signature. Each molecule has a spectrum of its own, which looks roughly like these, describing how each molecule interacts with light and where their absorption lines would fall in the spectrum of light, that rainbow I showed earlier. Combined, these molecular spectra form their atmosphere spectrum. And if we want to detect any of these molecules in an alien atmosphere, we need to be able to measure or calculate the spectra for each one of them. This is possible, but difficult, and requires a lot of lab work, often in dangerous conditions, and a lot of computational work, which is what I do, and that requires very large computers and many years of simulations. But even if we did become able to detect any of these molecules perfectly, these molecules on their own wouldn't necessarily indicate life because they all have false positives, by which I mean non-biological sources that can also emit these molecules into an atmosphere, such as volcanism and photochemistry. Basically, most of the atmospheric gases that life loves, examples of which are here in the first column, are also produced by non-biological sources, which you see on the last column. And this isn't some cruel astrobiological coincidence. This false positive problem happens because the chemical potential energy gradients that life loves to exploit are also easily exploited by geochemical processes. Basically, these molecules are great and I love them, but chemically speaking, they're quite easy to make. And so the detection of these molecules in isolation in an atmosphere wouldn't necessarily indicate life. So how do we solve this possible confusion? Well, there are two solutions to this false positive problem. One is to carefully consider context. For example, oxygen on its own may not be a particularly good biosignature. For example, if our sun had different levels of radiation at critical wavelengths, or if our oceans were evaporating from a runaway greenhouse effect, or if we had more carbon dioxide and less volcanic emissions, or just if the trace gases in our atmosphere are different, then large amounts of oxygen could accumulate in our atmosphere without any need for life. And then oxygen on this planet would be a false positive for life. But fortunately for those alien astronomers, in the context of our planet and our sun and the other components of our atmosphere, oxygen is a wonderful, robust biosignature. But sadly, context is not always that easy to determine. Knowing which molecules form the chemical and atmospheric context for a given biosignature molecule is particularly challenging. So my old group at MIT tried to be really agnostic about this problem and came up with a list of all possible atmospheric gases that could form the context of a potential biosphere. And that list contains 16,367 molecules. So the first problem is that this list is quite long, but it's finite, so I'll take it. But the second problem is that we currently only have the tools to detect a tiny fraction of these molecules. And this means our ability to understand the chemical and atmospheric context of any biosignatures we detect isn't great, making it difficult to resolve these false positive scenarios for those popular biosignatures of life as we know it, like oxygen and ozone and methane and water. But life, as we know it, is likely only one island in the vast archipelago of possibilities for life. Our galaxy has a huge diversity of stars, and orbiting them are planets of every kind. Earth alone has given rise to billions of different species. So it's not a big leap to think that life itself can arise in a large array of unexpected forms, and that life will produce many strange biosignature gases beyond those that we're used to considering here on Earth. Which brings me to the other solution to the false positive problem, and that is look for the molecules that, although are less popular and maybe less pleasant, but are biosignatures with very low or no false positives, and so they need less context to signify life. So an extreme example here would be CFCs, really complex pollutants, or other signs of industrial activity, though that's obviously an edge case. My favorite of these strange biosignatures with low false positives for life is the phosphine molecule. However, when I first started working on phosphine over a decade ago, it was very much not considered a good biosignature. In fact, phosphine was only known for two things. One, as a marker for violent storms in Jupiter and Saturn. Phosphine is detected in the upper layers of these planets, but it is a little surprising to find it there because the temperature and hydrogen pressure in those regions are way too low for the formation of phosphine to be likely. But what happens, we understand it now, is that phosphine, after being happily formed in the hellish depths of these planets where its production is chemically favored, is then aggressively dragged up to the top by strong, violent, fast currents, surviving to much larger concentrations up top than we would have otherwise predicted, many, many orders of magnitude. So phosphine is really important for understanding the chemistry and dynamic of gas giants like Jupiter and Saturn, but it's much harder to sell it as a biosignature. And that's because the only other thing phosphine is known for is for being horrific. Phosphine is a highly flammable, extremely toxic, and outrageously foul-smelling gas. It interacts fatally with our oxygen metabolism, and so it's a really effective killer, which is why it's widely used as a fumigant, and sadly, also why it was used as a chemical warfare agent for over 100 years now in the First World War, and most recently by ISIS. It is also emitted into the Earth's atmosphere as an unfortunate byproduct of methamphetamine production. So pesticides, war, and meth, they are all unequivocal signs of life. But I wouldn't necessarily expect alien life to be fond of any of these activities. So at this point, phosphine still didn't seem like a promising biological molecule, just a really scary one. But as I was researching phosphine, I realized that for about 100 years now, there had been quiet but regular mentions of phosphine being found everywhere, which was very much unexpected. You see, on rocky planets like the Earth, phosphine is so prohibitively hard to make. It is so toxic to life when it is made, and it is so reactive with the radicals in the atmosphere that we shouldn't see it anywhere. And yet we do. We find it in trace amounts ubiquitously throughout the globe, and in weird places in strangely large quantities. Places like sewage, marshlands, rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, the feces of penguins, the farts of badgers, and actually in the intestines and excrements of most animals. And the one thing that all of these ecosystems have in common is that they're all anoxic or without oxygen. These are biological niches that are populated by anaerobic life that is not reliant on oxygen. On Earth, these environments exist, though they are poorly studied. And here, phosphine is not evil at all. It's only phosphine's relationship with oxygen metabolism that makes it so lethal. But for the majority of time that life existed on Earth, it didn't rely on oxygen. And so other planets with life less oxygen loving than our modern Earth could happily have phosphine as a popular biosignature. With that in mind, we ran innumerable simulations of future observations of potentially habitable planets to try and figure out whether phosphine could survive in a variety of hypothetical planets with oxygen-poor atmospheres, if it could be detectable in the near future, and if so, if it could be distinguishable from other atmospheric constituents. I spent my entire PhD using quantum chemistry and very fancy supercomputers to calculate all of the spectral properties of phosphine. And I found that it has a distinctive spectral fingerprint, which you can see here in black, that sets it apart from other molecules in here in color. And we found that with an observatory like the James Webb Space Telescope, which will launch into space at the end of this year, we could detect phosphine on oxygen-poor planets in the galactic neighborhood, orbiting a cool small star. So that's the most popular type of star in the universe. And in those planets, we could detect phosphine if it was created by life with at least these production rate values. Now, these are completely reasonable production rates to expect. They're comparable to the global rates of methane on Earth, and they're well below the maximum Earth production rates of phosphine found above places that have oxygen-poor ecosystems, like penguin colonies that have a lot of poop, or sewage plants. Now, on planets orbiting sun-like stars, we would find it harder, but still possible, to detect phosphine, but only in a few scenarios, namely the really puffy atmospheres you find on hydrogen-rich planets, and only if their life really liked producing phosphine. So to detect phosphine on a planet orbiting a sun-like star, so like an Earth twin, we would need something like a full sewage planet or an intestine planet, which I know does not sound particularly appealing, but I can assure you we would be disgusting to them too. So the takeaway here is that on potentially habitable exoplanets in our neighborhood, astronomically speaking, phosphine can be both detectable and distinguished from the rest of the atmosphere. And this made phosphine quite promising as a biosignature. And to make it even more appealing, it seems to have no significant false positives for life, as long as it's found on rocky, temperate planets. So definitely not a sign of life on Jupiter. We came to this conclusion by considering every false positive scenario we could conceive of. We first looked at standard chemical processes for making phosphine, but we found that in all cases, the formation of phosphine was completely chemically disfavored. So at that point, we looked at more extreme situations like lightning or volcanism and meteors. And we found that even in the atmosphere types, which should be the most favorable for phosphine production, only a negligible fraction of phosphorus could turn into phosphine, and always many, many orders of magnitude below any detectable amounts. So at that point, we looked into increasingly more implausible scenarios, and none delivered any substantial false positives for phosphine. This means that given our current understanding of rocky planets and their atmospheres, we now had this tweetable conclusion for our work that said any detectable amounts of phosphine on a rocky planet can only be explained with life. Now, when I submitted this work for publication in 2018, I thought this was a cool conclusion, but it wasn't controversial at all, because it was just me describing a totally theoretical, hypothetical situation. I was imagining a distant planet, an anoxic tropical paradise with a rich biosphere producing tremendous amounts of phosphine that we might one day be able to observe. Some of you might now know that phosphine turned out to be a little more exciting than I had initially envisaged, because a few months after I submitted this work, an astronomer at Cardiff called Jane Greaves reached out to me asking for help with interpreting an observation seen here in white. And many months later, a follow-up observation shown here in orange that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on the planet. Jane knew this was very strange, but needed a phosphine expert to know how strange. And that's how our collaboration began. Now, the notion that phosphine, a molecule I had claimed to be a very promising biosignature with almost no false positives for life, might be present on Venus is, of course, very exciting. And the press thought so too. But before we jump on life as an explanation, I should point out there's still so much about Venus we don't understand. So all we really know is that something strange is happening. Currently, there's plenty of controversy surrounding this potential discovery, which I'm happy to discuss here. But ultimately, we need to address the primary uncertainties of the discovery. Namely, is the signal definitely real? If it is it unambiguously phosphine? And if it is, what or who is making it? Some reanalysis of our data find that with specific analytical approaches, the signal seems to disappear altogether. But other independent analyses find instead that the signal is indeed real, weak but significant. I am convinced that the signal is real, but is it phosphine for sure? Phosphine is currently our best candidate for the signal, but it's such a strange molecule to find on Venus that other alternatives have been proposed, such as sulfur dioxide, which in some circumstances can mimic phosphine spectral fingerprint. So how do we answer these questions? First, we get more data. I am currently analyzing data from Venus at different wavelengths, and others are also. And as we get more data from Venus, we can also improve our models of the Venusian atmosphere, and they can help us make sense of the few observations we do have. The problem here is that little is still known about phosphine on planets, and even less is known about Venus, so it's really difficult to interpret these observations. To make the most of both future models and observations, we will definitely need better fundamental data that can not just describe phosphine, but every other strange atmospheric component of Venus and how they interact with one another. This toolkit is vital for us to understand what is happening on Venus, and I am working on it. But what I want to highlight at this point is how a virtually unknown and quite unusual and disgusting molecule became such an important piece of the puzzle in the search for life beyond Earth. And phosphine is just one molecule, Venus, one planet. Even if it turns out that indeed we have found phosphine on Venus, this will not be the last time we find a potential biosignature on a planet beyond ours. So the question is, how do we become better prepared to characterize planetary atmospheres in the future? And that's what I spend most of my time working towards. Remember those thousands of molecules that could form the context of a biosphere? Sadly, we currently only have spectra for less than 4% of them, which means that for the remaining 96% of molecules, potential signs of life, we have no ability to detect them anywhere. Now, I do spend most of my time working really hard to solve this problem of missing spectra, but each molecule takes a really long time to understand. For example, take phosphine. We know its spectrum now, but that's partially because I spent my whole PhD simulating how it interacts with light and how we can detect it throughout the galaxy using quantum chemistry. But phosphine is just one of those thousands of potential biosignature gases. And I would love to repeat what I did for phosphine to obtain spectra for these thousands of molecules that are missing them, but I'm just one person. And to do phosphine, a single molecule, took a lot of sweat and a lot of tears and a lot of computer effort and 4 years of my life. Which means if I was going to tackle those remaining thousands of molecules that have no spectra at the same rate, it would take me over 60,000 years, which is too long. And I came to this realization a few years ago when I was writing my PhD. At the time, I was also the head of education for the Twinkle space mission. The Twinkle space mission is planned as a small but very impressive UK satellite for the characterization of planets. In this mission, I delivered all the educational outreach programs for the mission, but I was doing this while I was also training as a high school teacher in a London school, also high school and middle school. I should point out this was a terrible decision because it turns out teaching is many, many orders of magnitude harder than being an astrophysicist. Having done both, I can attest. And while I was trying to teach as best as I could, I noticed that whenever my research was mentioned in my classroom, the students and I would get into super interesting discussions, which made me think, what if I wasn't working on these thousands of molecules alone? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own kids to research molecules with me and 3 junior scientists who agreed to help. And this is the first cohort of students, which I split into 3 groups, each dedicated to studying spectra of a molecule crucial for understanding exoplanets and their host stars. So I would like to introduce to you Team Titanium Oxide, Team Acetylene, and Team Methane. These incredible kids learned astrophysics, quantum chemistry, programming, scientific writing, and performed original research on these three molecules. They went from being my high school students to my official scientific collaborators and became my co-authors on multiple peer-reviewed published papers. These students you see here then became mentors for next year's students and those the year after, and so on. I hired someone to replace me when I left the UK, so the program continues on without me. And since 2018, more than 100 school students have become published authors of scientific papers through the Orbits program. And this year, Orbits won the Neon Widening Access Initiative Award for outreach. Since we started collecting statistics, we also found that students who participate in Orbits are more likely to take advanced STEM classes when given the choice. So this is a really encouraging sign for the impact of the program, though I should point out small number statistics. To continue this sort of work in the US, I then became the director for the Harvard-MIT Science Research Mentoring Program, or Srmp. I have actually just stepped down as director to focus on my research, but we still have a small team of incredibly dedicated scientists and educational experts running the program. The general principle is that we recruit about 3 to 8 junior scientists, so mostly postdocs and senior Ph.D. students, and we help them adapt their current astrophysics projects to benefit from student collaborations. We then hire, train, and pay a salary to 10 to 15 local high school students and assign them to mentors with whom they perform original research throughout the academic year, not just in astrophysics, but also climate science. After all, the Earth's atmosphere is just another planetary atmosphere. At the end of the program, we organize a scientific symposium for the students to present their research to the community. And the caliber of research that the students perform is extremely high. For example, Srmp students Kartik Pingley and Jasmine Wright finally published their work in January this year on their collaborative discovery of a multi-planetary system. This was not the first, or indeed the last time Srmp students have become co-authors of peer-reviewed scientific publications, but this incredible achievement was covered in press all over the world, including CNN and the Smithsonian magazine. And here is Jasmine talking to local news of the Center for Astrophysics earlier this year. I also run another program called JURA, or Junior Research Award, which is aimed at high school or undergraduate students that have extraordinary potential, but don't quite fit into these programs. Like Emmeline here, who's an incredibly talented student that couldn't qualify for Srmp because she lived too far away, just in the wrong postcode. And she worked on cataloging planetary disks. I am currently supervising Asma and Kara to further improve the phosphine spectrum, and they were both just out of high school, so they also couldn't qualify for Srmp. And we also have Megan, who's been working on a full investigation of the detectability of potential pre-biosignature gases, such as hydrogen cyanide, like I mentioned earlier. And recently, we're also joined by 2 remote undergraduate students, Zara and Lorenzo, who are working on a large-scale molecular database from London. So it isn't just me anymore. By training and supporting students, we are now able to work on obtaining the molecular fingerprint for several new molecules, putting a small dent on that list of thousands of potential biosignatures that still need spectrum. When it comes to understanding these spectral fingerprints of biosignatures, I now calculate that if everyone I train joins the effort, and the kids do very legitimately have other career plans, but if they didn't, then we could get all the spectra we need in not 60,000 years, but about 2 decades, which is really encouraging. Because whether you're looking for life by searching for these unusual biosignatures like phosphine, but there's many other weird molecules we're just beginning to understand, such as isoprene. But whether we're looking for these weird biosignatures, which are strange and would only be present in atmospheres in tiny quantities, but have no significant false positive for life, or whether we look for the pleasant and abundant potential biosignature gases like oxygen and methane, but need to consider way more less abundant molecules to consider them to give these biosignatures context and resolve the false positive scenarios for life. Either way, the fact remains we must be willing and able to consider many, many more molecules, whether they're abundant or not. Ultimately, as much as I like phosphine, and I love it, and as much as I like the more traditional biosignatures like oxygen, which I do, I don't expect that the detection of life will come from a single molecule. As the Venus story shows, the detection of life will likely be uncertain. And that uncertainty will only be reduced if we're willing and able to both detect and understand more molecules, even if they're not popular or pleasant or abundant. Because just because a molecule isn't abundant, it doesn't mean it's not significant. It may be harder to detect a trace gas that has a small impact on its atmosphere spectrum, but if we really want to understand exoplanet atmospheres, and specifically, if we want to increase our chances of knowing if they're biospheres and actually confirming life, we have to be willing to consider the big picture, not just a few promising molecules, but all possible molecules that can together help us paint a holistic picture of an exoplanet atmosphere. So we need a lot of people because there are billions of stars in our galaxy alone, with billions of planets orbiting them. And these planets could contain trillions of life forms, releasing thousands of molecules in their atmospheres, just waiting to be detected. But this is all much more work than the current cohort of scientists can handle. Ultimately, it won't be the next generation of telescopes that will revolutionize astrophysics, but the next generation of people. And it is our job to equip them with the tools and opportunities to participate in this journey if they would like to navigate it, which is why I'm so thankful to you, who I think have the most laudable job in the world. So thank you. But looking for life is an interdisciplinary science. We definitely need astrophysicists, engineers, biochemists, and quantum chemists, and teachers. But when the time comes, we will also need philosophers and poets if we're ever going to make sense of it all. So the last thing I want to show you is what happens when you add musicians to this list. This deceptively simple phosphine spectrum I painstakingly simulated over years of work is actually formed from the collective force of 16.8 billion tiny spectral features, absorption lines that I calculated. And each of these individual features represent a very particular form of quantum vibration of the phosphine molecule at very specific frequencies of light. The underlying complexity of these vibrations, these frequencies, is quite hard to visualize and even harder to understand. But vibrations of particular intensities and frequencies is exactly what music is. So I recently collaborated with the composer David Ibbott, who was able to map the spectral behavior of phosphine to the audible range, effectively sonifying phosphine's quantum behavior. So this is what phosphine looks like, but this is what phosphine sounds like, transformed into a solo cello piece that captures the complex row vibrations of the quantum behavior of the phosphine molecule when it interacts with light. Recently, I was lucky to hear Minjin Chung perform this piece. And so now I will invite you to lean back and relax towards the end of this talk and listen to the wonderful sound of the terrifying and mysterious phosphine molecule.
Anyone else? What? Oh, it's both of them.
I hope you enjoyed the sound of phosphine as much as I do. But here are the main takeaways of this talk. To be able to characterize exoplanet atmospheres and ultimately to detect life and find a biosphere, we'll definitely need bigger and better telescopes. And within the next few decades, we will be able to point these bigger and better telescopes at a potentially habitable planet. And we'll be able to look at these planets' atmospheres. But these atmospheres could contain many more molecules beyond those that we understand. And currently, we are not prepared to both detect and interpret the presence of most molecules on an exoplanet. So my biggest professional concern is not that we will fail to detect an inhabited planet in our lifetime. My biggest professional concern is that we'll point our very expensive telescopes directly at an inhabited planet and just not have the tools to know it. So it is only by collaborating with people of all ages and fields, and by using state-of-the-art science to consider all possible atmospheric molecules, that we will be able to provide the tools to understand alien biospheres so that one day together we'll know life when we see it. Thank you.
Thank you so much, Clara. That was incredible. I think we have a lot of questions in the chat. But as always, we love to start with anyone who would like to share a verbal question. So if you would like to share your question directly with Dr. Sousa-Silva, please use the raise hand feature in the lower right hand of your screen, or you can just raise your hand, though we can't see all of you. I see Jamie, so I'm going to go ahead and call on you, Jamie. And then Sony Titus, we'll go to you after that. Go ahead, Jamie, and ask your question.
Hi, thank you so much. This was like probably my favorite Thursday Think ever. So thank you. I learned so much. My question is, can you say more about how the musical piece was taken from the spectrum or from information about phosphine? I just like that like blew my mind, as I think other people in the chat kind of said too.
So I can only explain so much. The composer is wonderful at understanding complex science, but I really struggle with music. I'm not a very musical person. And so a lot of the things he explained to me, there were like a lot of jazz terms, did go over my head. I do know that when he first sonified phosphine, Minjin, the cellist, came back to him and said, David, some of these are physically impossible. They cannot be played. And so some of the features had to be simplified. But generally, there's a lot of quite repetitive patterns in quantum chemistry. And so those played really well at making effectively harmonies. And so I was surprised with how good it sounds. I saw that in the chat, some people had mentioned, other molecules and the sound. And that's actually a project that we're working on, is the sound of Earth's atmosphere. So the collective spectrum of all the molecules in Earth's atmosphere throughout history, and how it changed as different molecules and different life appeared. And that is orchestral. Each molecule gets its own sound. And so it's really interesting to see how something really complex is much easier to hear. Our ears much better at receiving complexity than most of our other senses. And so David really exploited that. I wish I could give you the actual terms of what he said, but I'm afraid I no longer remember.
That's okay. Thank you so much. Really appreciate it.
You're welcome. Thank you.
Maria, I see your hand up. Go ahead, Maria.
Yeah, I wanted to have a better understanding of how you engage the students, because my husband's a chemist. What you were doing with those spectra is very complicated. It's complicated to look at that and understand it, let alone for a student to sort of integrate everything that and do data output. And you said that they got some publications out of it. So I want to know kind of how you made that happen. And there were some other people in the chat who really wanted to understand better how you engage the students with this. And the music was great too. Thank you.
Thank you. I'm glad you liked it. I've learned a lot of lessons on how to work with students, mostly by making a lot of mistakes. But there were some tricks. For example, when I was doing quantum chemistry work with them, I just didn't use the word quantum for the first 3 months. And then once they had done it, I was like, you're a quantum chemist now. And it was too late to be scared. They'd already done it. So that was one trick. The thing that worked every time was, once you got the first set of students, have them teach and mentor the others. It was a lot less terrifying. In the first year I did this, I was also a teacher, so I was able to support them in class. So that made it much easier. Since then, the fundamental kind of basis for the success of these programs has been having a supportive teacher in the school that can play that role. But I made a lot of mistakes. For example, I made most of the classes, the meetings, the research meetings with the students after school, because I thought, that's when it makes sense. And then found out that several of the students that I thought would have been great couldn't do it because they all worked. This was a really poor area of North London, and they contributed to the mortgage. And I felt terrible that it didn't even cross my mind. So I managed to work with their schedules to do meetings during the day. And I just paid extra to the scientists who are coming into the school to leave in the middle of the day to come to the school. So I was able to adapt, but these were all lessons that I kind of had to learn by making mistakes. But it is hard. I have found that most of the mentors struggle to keep the students focused on the big picture. I was surprised how quickly the students become really comfortable with technical terms about the niche research they're doing, but they lose ability completely to explain it to anyone else and to understand it in a wider context. And so training the mentors themselves, the scientists I bring in, to continuously connect the minutiae of the work the kids are doing to the wider context, the big questions that are being answered, has been very valuable. But it is tough. I spend half of my time soothing students and encouraging students than I do, teaching them science.
I think there's a lot of balance with that right now of soothing and teaching science. Thank you for that answer, Clara. We have two raised hands. We'll go to Jonathan Levine first, and then we'll take Christian's question. Go ahead, Jonathan.
Hi, first, thank you for sharing. My question was, when you went about selecting phosphine, right, you talked about some of the factors that you considered in deciding to use this marker and to look for ways in which we can analyze the spectra. For that list of 16,300 some odd markers, how do you go about finding the next best phosphine, so to speak? And how do you narrow down that, vast list in terms of selecting what some other good biomarkers would be to find life?
It's hard. The general principle that we followed was realizing that we already know that physics is a set of universal laws. We know chemistry is a set of universal laws, but we don't know what the universal laws of biology are. But we do know that however different alien life may be, it still only has the periodic table to use. So that's a scary large number of combinations, but it is all that they can use. And then we know what are the most popular atoms in the universe, and their distribution seems to be reasonably constant throughout the galaxy. So we start with those. And then we know that molecules that get too big, they struggle to be volatile, so they're not good gases. And so they're never going to be in atmospheres in a large amount. So that narrows the list again. So we narrowed by kind of popularity, by which I mean just literal popularity in the universe. And then we narrow again by the ability to actually be in an atmosphere. And then we narrowed again by looking at the molecules that could be made. So just the possible chemical combinations. And that was already a huge a reduction in the total number of possible molecules. But the next step gets really complicated and collaborative. You basically have to look at a planet by planet. Given the radiation of the star that hits that planet, what molecules would be destroyed versus what molecules would be created. Given the temperature and the thickness of the atmosphere on that planet, what molecules could be in the atmosphere. And then given which molecules we do see, what other molecules could coexist in that atmosphere. We also have biologists that looked at potential bases of life, so carbon-based life or silicon-based life, but even within these, what kind of choices, chemical choices life might make. Because some choices that life makes, evolutionarily speaking, really restrict the available biochemistry that would maintain that life. And so we call these islands of biochemistry, and these also reduce the number of molecules. But I don't even try to rank them because we know so little about these planets. And a planet where phosphine is a good biosignature, like on Earth it would be if there was no oxygen, is not like Jupiter, where Jupiter has phosphine and there it's not a good biosignature. And so it becomes context specific. So we don't try to rank them. And my general approach is to try and be as little Earth-centric as I can as a human, which, it's a losing battle.
Thank you.
Also, I should point out, sorry to interrupt, that I can post a link not just to the YouTube video, but I'll post a link to the educational paper that I wrote about my experiences in orbits, which also describes some of the difficulties I had and how I overcame them. And it's a free paper and there's no paywall. So Maria, to answer your question, I can post that in.
That'd be wonderful. Thank you so much for sharing that. Right, we still have quite a few hands raised, and we have several questions as well in the chat. So Christian, we'll take your question next, and then Sony Titus, we are very happy to have you back, so we'll go to you, and then James. So go ahead, Christian.
Hey, thanks for joining this. It's been super interesting. I recently read a science fiction book of which it was like talking about extraterrestrial life, and ammonia was the gas of choice for like the atmosphere. And I was just wondering how likely or possible that is, considering like the shape and how nitrogen and phosphorus are similar, if that's like something that we know is feasible or not.
Yeah, excellent question. So ammonia is very much a promising biosignature. It has a very similar pyramid structure to phosphine. So actually, when we're missing data for phosphine and how it interacts with other molecules, we often use ammonia as a proxy. So they have a lot of structural similarities that we find useful. Ammonia is a lovely molecule, a popular biosignature. Its only problem is that it's significantly easier to make than phosphine. So although it's a very popular biosignature, it is much, much more hard work for us to figure out whether it is life or geochemical processes that's making it. That doesn't mean we shouldn't look for it, and we certainly do. But it just requires a lot more context, which means more molecules, which puts us back to the same problem.
Great.
Awesome, thank you.
Thanks, Christian. Sony Titus, go ahead.
I was reading an article a couple of weeks ago about the probes that NASA funded recently to go to Venus. They funded two, I believe. And some of the discussion centered around whether about life in Venus, where would it exist? Because the surface conditions on Mars, on Venus, are such that they don't think it could exist. So the possibility of life existing in the atmosphere of Venus. So it was interesting when you touched upon that in your presentation. What would be your guess if there were life because of the detection of phosphine on Venus? Where would it be?
So these missions, Veritas and Da Vinci, were selected by NASA. We have been disgracefully neglecting Venus for many decades, so I was very pleased. There's also Envision from the European Space Agency. And together, these are incredible missions that will solve a lot of the many mysteries of Venus. One of the things they'll be looking at is exactly this notion of the habitability of Venus. We have known for a long time that the surface is absolutely uninhabitable, and that's by any life form, no matter how imaginative we get, because complex chemistry simply cannot survive the temperatures and pressures of the surface. But it is the clouds of Venus, where the temperatures are mild and the pressures are very similar to that on the surface of the Earth, that have the most promising habitat. And coincidentally, it's also where we found phosphine. We didn't find it outside the clouds. We only found it in the clouds. So that's one of the kind of more exciting coincidences, perhaps, but one of the more exciting aspects of the potential phosphine discovery. Now, how do we get life in the clouds? If there were a lot of journalists on this call, I'd be a lot more careful, but I'm happy to speculate a little with what we know. So we know that Venus used to be habitable. It used to be a really lovely place, but it had a runaway greenhouse effect, no fault of their own in their case. So maybe there's a lesson here somewhere for us. But they did have a tragic runaway greenhouse effect that rendered it mostly uninhabited. But if there was life there before this runaway greenhouse effect, then a massacre occurred, a planet-wide massacre, and only those life forms that were able to remain aerial, so remain in the clouds without ever coming down, would have survived, or any species that adapted to that would have survived. So if there's any life on Venus, it has to be in the clouds, and it has to be in the clouds their entire life cycles. They must never leave the clouds. And this is interesting, of course, and in my wildest dreams, I imagine these kind of floating Venusian manta rays, but we have no idea of the level of complexity or how they would live. Certainly, if the biochemistry of this life is anything like ours, it is a tragic existence that I wouldn't wish on anyone, because the clouds of Venus, although the temperature and pressure is nice, really nice, They are very acidic, more acidic than the most acidic places on Earth. And they have very little water. They're drier than the driest place on Earth. Even our most capable and competent extremophiles on Earth would not make it in the clouds of Venus. And so my dearest hope for our Venusian neighbors is that their life is nothing like ours. And they spend their lives happily in the clouds, sadly unable to see the night sky because the haze in the Venusian clouds is so thick. They have never seen stars or planets. They just know there's light coming, and unless they discover radio or something, they don't know we're all here. And so I do spend a disproportionate amount of time in my life considering those potential Venusians, but we know very little about what they might be.
Thanks for that question, Sony. I think you also answered a lot of the questions in the chat around wanting just to know a little bit more about the conditions that might support life on Venus, and generally what the conditions of Venus are, both terrestrial and up in the clouds. So thank you for your answer, very thorough answer, Clara. We'll go to James Anderson and then Joseph, and then we'll take some questions from the chat. Go ahead, James.
Hi, Clara. This is great so far. It's really awesome to talk to you. I teach astronomy in my school, and my students are always wondering about, complex life, alien life, and they always think alien life with communications and starships and stuff like that. And I talk about the Fermi paradox with them, and the likelihood of, complex life, including us, surviving for a very long time it's kind of, out there, and it's limited. So it's really cool to have phosphine detection will pretty much determine whether or not there could be life or possible life on the planet. But I was wondering, is there like another molecule paired with that would enhance the chance of more complex life, or life, at least maybe even on land, like ozone, even though it can be created other ways, or maybe a combination of a couple of other molecules that may lead to, your thought that maybe there is more complex life than just maybe simple bacteria or something like that?
It's a great question. So I'll touch on the complexity part of the question first. We don't know how complexity arises and how that combines with the molecules that you produce, and exactly which scenarios restrict complexity or not. But certainly in our simulations, when we choose particular paths in biochemical evolutionary journeys, some of those lead to very restrictive biochemical spaces, we call them. And so we do think there are choices life can make, not consciously, of course, that will restrict the complexity. And when it comes to environment, we don't know if a pleasant environment will lead to more complexity than another. Evolutionary pressures from a difficult environment may lead to complexity, but they may also squash that complexity after a certain point. The best thing we've got so far is something like phosphine or other molecules that have low false positives. They have low false positives for a reason. It's because they're really hard to make. In the case of phosphine on Earth, but isoprene, and there's a few other molecules I can discuss, they are made only by quite complex behaviors. So the universe doesn't like to waste. It doesn't make things at a cost. But life is willing to sacrifice for what it sees as a good reason. So in the case of phosphine, for example, all the life that makes phosphine, and we still don't understand those processes completely, but we know they must make it at a calorific cost. That means it has to be worth it. And usually those behaviors, and the same happens with ammonia and a few others, on life on Earth, those behaviors are complex. They tend to be things like communication. In the case of isoprene, the trees use it to communicate danger. And so when you're trying to communicate, you want to make sure that you're producing a molecule that won't be confused by something that is already in the environment. And so you want to make something that is really, really difficult to make. And so you're willing to expend energy to make it. And this is not something the universe makes easily. Life does. In the case of phosphine, it could be for defense mechanisms or attack mechanisms. Again, extremely complex behaviors. Some people have postulated that phosphine is used as a part of a bartering economy for phosphorus, a limiting nutrient for life on Earth. And if so, that's economy. So that's very complex behavior. So the best we have so far is this notion of these molecules that are really, really hard to make. And so you need the sort of life that is willing to sacrifice. And that is a complex behavior. But this is very niche and the best we've got so far. We, as you can imagine, know very little about alien biology. And so it's all speculation at this point.
All right, go ahead, Joseph.
I had a kind of similar question, but I'm just a little still confused because like the name of I love the name of the song, which was like Life Anaerobic, but on Earth, I feel like it sounded like you were saying phosphine is a signature of anaerobic life, but like on Earth, we don't think of anaerobic life as being like complex in the way that like you can, interact with it, like that it could form a civilization or something like that. So are there scientists that are proposing like anaerobic life out there that could form a civilization, or like that's my question, I guess.
So we don't know what would have happened to the complexity of life on Earth had oxygen not killed the majority of life that existed on Earth when it first started. Certainly, it will be very difficult to have a conversation with the anaerobic life in your gut, though it is a very complex system. It isn't complex in the way that we could have, pen pals with. On Earth, anaerobic life is very much second-class life. They don't have the chance to thrive. They're surrounded by an extremely toxic gas, and that's oxygen. So we have created a system that is really not welcoming, not hospitable to anaerobic life. We hope, specifically my team and the people who work with me on anaerobic life and the signs of that, we hope that other planets that don't have oxygen as a primary atmospheric component may allow anaerobic life to develop more complexity when they're not being squashed by oxygen. We don't know. There's plenty of biologists that believe that it was the oxygenation that opened up our biochemical space for complexity, but we don't know. We have a very small sample size of complex life, and that's just one on Earth. And we try to expand that by considering that Earth has been many planets and what kind of life it had before. But until we can find more life, it's hard to know. It seems like complexity is not inevitable, even though I believe life is.
So Clara, along those lines, we have a question in the chat from Jerry Citron, who would like to know a little bit more about the mechanism of why phosphine is so toxic to aerobic organisms, and particularly aerobic bacteria, and not to anaerobic ones.
So phosphine bonds with the ion inside the cells. We're going to reach my limits of biology pretty quickly. I do have a slide somewhere about this, but basically it stops the shuffling of electrons along the cell that eventually leads to the production of ATP. And when you block this shuffling of the electrons, so you basically have these little molecular transformers in the cell. And when you stop this and you stop producing energy, that will actually kill you alone. And phosphine is particularly cruel because that's not enough. It also binds with the enzymes that usually deal with the waste products of energy production in the cell, hydrogen peroxide and radical oxygen species. And they are usually treated by the enzymes we have inside and outside of mitochondria, but phosphine bonds with them and stops them from being able to process the waste products. So actually, phosphine kills in multiple ways that are all involved with the oxygen metabolism. And so it's pretty cruel.
Thank you. So Astrid Helfant in the chat would like to know your thoughts on life on Mars. So we've heard a lot about Venus, and I think it's the first time that many of us are hearing about potential life in the clouds on Venus and phosphine as an indicator for that. But do you have some thoughts about life on Mars?
If I had to, plan a holiday outside the solar system, outside the Earth, I think Mars is so bad, I'd rather be on Venus because although Venus is terrible, it at least has a thick atmosphere. Mars can't even protect its surface from radiation. And so Mars is a tough one for life. There can still be some subterranean life, but it's just a very tiny planet. And so I don't want to say anything too bad about Mars, because once I did, and I had all of the Elon Musk fans be very angry at me online. So I'm being very careful with how I speak about Mars. You know, I have no favorite planets. They're all equally loved like children. But if I had to choose, Mars will be low on my list for habitability, particularly compared to places like Titan, the moon of Saturn, that has a thick atmosphere. Basically, I think having an atmosphere to protect and create an environment where life can thrive, even life totally different from ours, is a higher priority than having a planet that is not actively harmful to us. I think as humans, Mars seems more habitable because it doesn't immediately kill you. But for life to thrive, it needs more than just a place that isn't boiling. It needs protection from the sun. So Mars, it's tough. There could be some subterranean life. We have been looking for ages. You know, we had a probe that went down a few centimeters. We didn't find anything. So then we sent a longer probe, didn't find anything. So now we sent a longer probe. Maybe we'll find something. But it's unlikely to be complex, and it would have to be subterranean. So I would love to find life on Mars, but if I was a betting woman, which I'm not, I would not put money on it.
Interesting. So I think there's been a lot of conversation about the presence of water and iron oxide, I think. And so Mars gets hyped up a lot. So thank you for those clarifying answers on that. We're going to turn to another question in this chat from Dash Anderson, who would like to know, are there solar systems orbiting perpendicular to our vantage point? And are those planets invisible to us if they never pass in front of their stars?
Excellent question. So the description of how we separate the light from a planet from a star really only works when the planet is going in front of the star. And that means we are missing out on all the solar systems, not just the perpendicular ones, but even the ones that are just tilted a bit, where the planet doesn't go in front of the star from our vantage point. Fortunately, we do have other detection and characterization methods. We, for example, are getting much, much better at just directly imaging the planets. So by covering the starlight with the coronagraphs, basically covering the starlight as much as we can, we are able to see cooler and smaller planets every time we have a new direct imaging mission. And then we'll be able to just directly get the spectra from the planet without having to extract it from the sun, which would be great because we lose a lot of information in that process. So there are other ways, but it is interesting to kind of figure out that we have these biases of what we can see. And all we can hope is that there's no reason why the planets that are facing us are special compared to those that are not. And so we can extrapolate those planets as a representative sample. So for those looking at the statistical incidence of habitable planets and the eventual statistical incidence of life, we should still be able to use this method. But yes, we have to use other methods to study planets that are not aligned.
Great, thank you. So we only have time for one more question, and we did have a couple of teachers in the chat ask a similar question. So the majority of our teachers here this evening and in our Math for America and State Master Teacher community are middle and high school teachers, but we have a small but robust group of elementary school science teachers, and we're very grateful to them for nurturing curiosity and passion for science in students at such a young age, and then sending them to us at the middle and high school level. And so they would like to know, what are some takeaways? This is from Michelle Layer in the chat. What are the most basic parts or some takeaways from tonight's talk that they can take back to their elementary school students?
So a lot of my public science talks actually started out very complicated and technical. And then I once did a class at a primary school, and I realized that it was much better to explain it that way to adults even, and certainly older students. And so I'm really thankful for working with primary school students. And one of the things I did with them, and I was surprised how well it worked, was I just had a lot of light bulbs, some that were LED, and so they had a continuous spectrum, and some that were mercury, or I had other older light bulbs have stuff in them, and so they basically have spectrum. And I had a little handheld spectrum, and I still have loads of them. So they're basically, this is a prism, but you can get these handheld spectrographs, and they're used, I think, by jewelers to detect, impurities and to figure out, how much jewels are worth, crystals and such. But they're really cheap on Amazon, and they're tiny and they're pretty robust. And then I would have the students look at the sea of light bulbs and say, this is a sea of stars. They all look the same, but they're not all the same. I would have them go around and look through the spectroscope. And some would have continuous spectrum, and I call those stars. And some would have emission lines, and I call those stars with planets. And so I really did introduce the concept of light and how when you break light, it shows up all these secrets. And that was my trick. And I know it seems crazy to talk about basically spectroscopy with really small children, but it's very visual and it's very beautiful. And I then had different atoms and molecules, and they had to match them. And so they really learned how to see the invisible notions of molecules and atoms through light, as long as they had a little spectroscope. And it was really cute and it looked beautiful. I just lowered the light in the room, and it was just a sea of stars with lots of kids looking for planets. And it's not entirely scientifically correct, but I figured by the time the kids figure out the oversimplification, they had learned so much science that I was going to call that a victory.
That sounds like a wonderful and really accessible and easy demonstration to get kids excited at any age. It sounds like a lot of people agree with that in the chat. Thank you for that suggestion. And thank you for your incredible talk this evening. I think many of us are inspired to learn even more about life in the universe, particularly on Venus and phosphine here on Earth, as well as in the clouds of Venus. So thank you again. And to our state master teachers who have joined us once again, always lovely to have you. I'm going to turn it over to Jen Cody to close us out. Jen?
Thank you so much for joining us tonight, and I hope you all had a wonderful time. I did.
Thank you. Good night.